At a certain instant of time, the velocity and acceleration of a particle are 2 meters per second. At a certain instant of time, the x component of the velocity of an object is 2.0 meters per second, and its y component is 3.0 meters per second, while the x component of the acceleration of the particle is minus 4.0 meters per second squared. Find the scalar tangential component of the acceleration and the scalar normal component of the acceleration relative to the velocity of the object. From this information, determine whether or not the object is speeding up or slowing down. So we are given the velocity of an object at a particular instant in time. The x component is 2.0 meters per second, and the y component is 3.0 meters per second. We're also given the acceleration of this object, which looks like it's pointing along the negative x-axis with a magnitude of 4 meters per second squared. From this information, we have to determine the scalar component of acceleration that is tangent to the velocity vector, which is also tangent to the curve on which the particle is traveling, and we have to find the scalar normal component of the acceleration relative to the velocity vector along the curve in which the object is traveling. Before we do this, we should recognize that the velocity and the acceleration are both in the xy plane. So it'll be very easy to construct a sketch of these vectors at this particular instant in time, and we could use our sketch to qualitatively determine the tangential component and the normal component of the acceleration relative to the velocity vector. With this, let's be careful in our sketch. So I'm going to go ahead and use some graph paper. The y-axis is drawn vertical. The x-axis is horizontal. Now, for perspective, let's superimpose the x-axes of both the velocity vector and the acceleration vector. So the y component of the velocity vector will be vertical, and we'll use this vertical axis to also represent the y component of the acceleration vector. We will look at the x component of the velocity vector on the horizontal axis, and at the same time look at the x component of the acceleration on the horizontal axis. This way, we could qualitatively compare the two vectors and see whether or not the object is speeding up, slowing down, or it could even be turning. Let's do a consistent scale on each axis. So on the x-axis, we'll have every 5 squares will correspond to 1 unit along the x-axis. Let's extend our negative x-axis a little bit. And we'll say 5 squares will also correspond to 1 unit on the y-axis. We see that the velocity vector has an x component of 2 meters per second. So we'll represent the velocity we'll draw the velocity with its tail at the origin, and we'll come out 2 units in the x direction, and then we will go up 3 units in the y direction to give us our velocity vector. We will label this vector v. The acceleration only has a negative x component, so we'll put the tail of the acceleration vector at the origin of our coordinate system, and we will go to the left 4 units. So that puts us right here on the x-axis, and I will label this vector a vector. By positioning the acceleration and the velocity tail to tail at the origin of this coordinate system, I could see pretty clearly that this object is going to be both slowing down and turning, because we'll have a component of acceleration that is opposite the velocity vector, and there is a component that's perpendicular to the velocity vector. To better illustrate that relationship, let's go ahead and draw a line on which the velocity lies. To help me with this, I'll just use a ruler. So here's our ruler that is parallel to the velocity vector. So the line on which velocity lies is given by these dashed lines. Let's continue this to the other side of the velocity so we can have a good perspective of the line on which velocity lies. There we go. Now that we have the line on which the velocity lies, we're better able to see the relationship between the normal and tangential components of acceleration. By projecting a line from the head of the acceleration vector down to the line on which velocity lies, such that it's perpendicular to the line, we're able to see the projection of the acceleration onto the velocity axis. Let's label this projection of the acceleration onto the line of velocity a sub t. And from trigonometry, this is the side adjacent to the angle between the acceleration and the line of velocity. So this is equal to the magnitude of the acceleration times the cosine of the angle between the acceleration and the velocity vector. Now, we should acknowledge that we're using a reference angle, so I'll put a hat on top of the angle. And because we're using a reference angle, we're going to have to keep track of our minus signs because the cosine of a reference angle is always positive. So to indicate that this is opposite the direction of velocity, I'll put a minus sign in front of our coefficient. Based off of what we've learned, we know that this is equivalent to the dot product between the acceleration and the velocity divided by the magnitude of velocity, or the speed of the object. Now, the side opposite to the angle between the acceleration and velocity will give us the normal component of acceleration relative to the velocity. Let's label that normal component a sub n. From trigonometry, once again, we know that a sub n is equal to the hypotenuse, which is the magnitude of the acceleration, times the sine of the angle between the acceleration and the velocity vector. Now, we also happen to know, based off of what we've done previously, that this is equivalent to the magnitude of the cross product between the acceleration and the velocity over the speed of the object. So we now have two expressions that can help us find the tangential component of acceleration and the normal component of acceleration. So let's measure that directly. In measuring it, I get about 2.4 meters per second squared. So let's write that down. We will say the tangential component is approximately minus 2.4 meters per second squared based off of our picture. Now, we might be off a little bit because this is a sketch. So things aren't perfect. But if our answer when we do it algebraically is really close to that, we should then feel good about the work we've done. Let's now measure the normal component to see what value we get. So measuring the normal component, I get the normal component of acceleration to be about 3.2 meters per second squared. Okay, so this is a good sketch. It's a good start. Let's go ahead and do some math now to see what we actually get. We said for the tangential component of acceleration, that is equal to the dot product of the acceleration and velocity divided by the speed of the object. Well, the acceleration is a vector with just an x component, which is minus 4 meters per second squared I hat. And we are going to dot this with the velocity vector, which has both an x component, which is 2.0 meters per second, and a y component, which is 3.0 meters per second. This is all divided by the magnitude of the velocity, which is equal to the square root of the sum of the squares of the components of velocity. Evaluating the dot product means that we take the sum of the products of the components of acceleration and velocity. We see that this last term is 0. And in the denominator, we have the magnitude of velocity, which is equal to the square root of the sum of the squares of the components of velocity. When we evaluate this, we get minus 8.0 meters squared per second cubed in the numerator. And in the denominator, we get the square root of, let's see, 4 plus 9 is 13 meter per second. We could simplify some units. A meter in the denominator cancels 1 in the numerator. A second in the denominator cancels 1 in the numerator. We now have minus 8.0 over the square root of 13 meters per second squared. This gives us a tangential component of acceleration being equal to minus 2.2 meters per second squared. Well, let's compare this to our sketch. In our sketch, we said the tangential component of acceleration was approximately equal to minus 2.4 meters per second squared. Now remember, this was a sketch. I was being as precise as I could on this screen, but I can't be perfect. Mathematically, though, this is very close to our numerical answer, our algebraic answer. So we should feel good that both answers support each other. So we've now found the tangential component of acceleration. We have to find the normal component of acceleration now. To find the normal component of acceleration, we'll have to evaluate the magnitude of the cross product between the acceleration and the velocity over the magnitude of the velocity, or the speed of the object. The cross product can be calculated by writing a 5x3 matrix and evaluating it. This matrix has columns given by the components of each vector. and the rows correspond to each vector. The second row corresponds to the components of the acceleration vector, which only has an x component. The third row corresponds to the components of the velocity vector, which has both an x and a y component. So to evaluate this matrix, we will take the products of one set of diagonals and subtract the product of the other set of diagonals. So this cross product can now be evaluated by taking the products of the diagonals and subtracting them. For the x component, we have 0 times 0 minus 0 times 3.0 meters per second. For the y component, we have 0 times 2 meters per second minus a minus 4 meters per second squared times 0. And for the z component, we have minus 4.0 meters per second squared times 3.0 meters per second minus 0 times 2.0 meters per second. Well, when we look at this, we have a 0 for the x component, a 0 for the y component, one term in the z component is 0. We get the cross product between acceleration and velocity to be equal to minus 12 meters squared per second cubed. And this is in the z direction. And it makes sense that it's in the z direction, since because acceleration and velocity are both in the xy plane, when we take the cross product of those two vectors in the xy plane, the result is a third vector that's perpendicular to the xy plane, which would be a vector that is parallel to or anti-parallel to the z-axis. Well, now that we have the cross product of acceleration and velocity, let's evaluate its magnitude. And for this problem, the magnitude is very simple to calculate. We have only one component, so the magnitude of this is 12 meters squared per second cubed. Now we're ready to find the normal component of the acceleration. Remember, the normal component of the acceleration is the magnitude of the cross product, the acceleration and the velocity, over the magnitude of the velocity, or the speed. So this is 12 meters squared per second cubed over the square root of 13 meters per second. Let's simplify some units. A meter in the denominator cancels 1 in the numerator. A second in the denominator cancels a second in the numerator. And also plugging into my calculator 12 divided by the square root of 13 gives me 3.3 meters per second squared. Well, let's compare this value to the value we got from our sketch. Here we have 3.3 meters per second squared. In our sketch, we got 3.2 meters per second squared. That is really good. Our sketch got really close to our algebraic answer. And what that means is we use the sketch as a reality check. And for me, we got the confirmation that we did the correct work. So we could rest assured that we have found the normal component of the acceleration to be 3.3 meters per second squared, and the tangential component of acceleration to be minus 2.2 meters per second squared. And since the tangential component of acceleration is negative, that means it's opposite to velocity. And as you can see from our picture, the acceleration tangential component is opposite to velocity. So this means that our object is slowing down.